So what we're going to do here is use Kirchhoff's loop and junction rule along with equivalent resistance in order to analyze the circuits to get an idea of what do we know and what can we find about each of the components in the circuit. We'll also use Ohm's law in this case. So circuit 1 is going to be a series circuit. We know it's a series circuit because I can draw a single loop that goes through every single one of my components. Circuit 2 is a parallel circuit, and that's because I can form a loop that goes through the power supply and each of my resistors independently. So that is going to be a parallel circuit. Circuit 3 is a complex circuit because I can go through series from my power supply through R1, but then I reach a junction, and then R2 and R3 are actually in parallel with each other before we would be able to come back and go back to our power supply. So we're going to take a look at each one of these individually. So we're going to analyze this series circuit first. So to refresh our brains, some special things about our series circuit is that our current is the same everywhere. And our current is the same everywhere in the circuit because of Kirchhoff's junction rule. Because there are no junctions. Remember, a junction is when current comes in and then splits. Because there are no junctions, there's no splitting, so the current has to be the same everywhere. Define I0 as the current coming out of my power supply. And then I1 to be the current through R1. And I2, the current through R2, and I3, the current through R3. And because there's no junctions, that tells me that I0 has to be the same as I1, which has to be the same as I2, which has to be the same as I3. So that gives me a lot of information, because if I know the current in any one location, then I know the current everywhere else. When we go to analyze potential, that is Kirchhoff's loop rule, and it tells us in a loop, the voltage rises must equal our voltage drops. So when you start, say it's your power supply, let's assume that the ground side of our power supply, the negative side, is at a potential of 0. What happens is you go through that power supply, you're going to gain potential, so we're going to have V0's worth of potential. And that what we assume is that everywhere that we are in contact until we encounter resistance is at the same potential. So that's going to be V0's worth of potential when you reach R1. And then there is going to be a voltage drop, which I'm going to call delta V1, across R1, because some of our energy is going to be converted from kind of this electrical energy into heat through that resistance. So that this point right here at the end is now V0 minus delta V1. And then if I come along this wire, this whole wire here also has to be V0 minus delta V1. And then when we counter R2, there's going to be a voltage drop, delta V2, through that resistor as we convert more of our energy into heat. So that this point right here is V0 minus delta V1 minus delta V2. So we've lost more energy. And then we come back around here, and that whole thing's going to be V0 minus delta V1 minus delta V2, because remember, we are assuming that our wires have no resistance. We are going to have a drop in potential, delta V3, across that resistor. So this point right here is V0 minus delta V1 minus delta V2 minus delta V3, which is then connected to this ground wire. So that all has to add up to 0. So that really tells us that whatever our potential is, our EMF from our power supply, that it is getting divided up between each of those resistors. So resistors are sometimes called voltage dividers because they divide the voltage of the power supply into pieces, so that we end up with our voltage of our power supply has to be the sum of all of those individual voltage drops. So that, because it gets divided. So that is kind of some of the information that we can learn about the series circuit. So what happens is that when you add more components, all of your potential still has to add up to V0. So each of these is going to have a slightly smaller voltage drop than it would have originally. And our total series has more resistance. So the equivalent resistance for series is going to be R1 plus R2 plus R3 plus however many of those are, which we can write as Req is equal to the sum of Ri for each of the individual components. So as you add more components, your overall resistance goes up. And so what ends up happening is your current has to go down, because the current in our circuit with Ohm's law, I0 has to be V0 over Req. So that's just kind of a review of what we know. Now we can use Ohm's law for every single component. So I also know that delta V3 has to equal I3R3, and so forth. So let's switch over to our parallel circuit and go through a similar analysis. So with our parallel circuit, once again, we have different loops that we can go through. So I can write a kind of the current draw from that power supply, and then there's going to be a current through each of these branches, I1, I2, and I3. So because we are encountering splits, every time you reach a junction, your current is going to split off into a different kind of branch. Now, this one is kind of funky because you have these kind of partial branches. So like I could call this one like I4 is the current right there in that branch. So technically what's going on is I get that I0 has to equal I4 plus I1 for this branch right here. That's coming in. And then at this junction here, I4 is splitting up into I2 and I3. So I4 is equal to I2 plus I3. So if I was to kind of come over here and plug that in, I get that I0 would equal I1 plus I2 plus I3. So even though this is a little funky with this extra little kind of like partial current right there, what this tells me is that the current that is being drawn for the battery is the sum of I1 and I2 and I3. Now, this is kind of weird and funky because the more components I add, the bigger and bigger the current draw is. This is not a current divider. It looks like it is, but it's really not. It's more like a current adder. And that's because my potential in each of these branches is the same. Because if I assume I have 0 here on the ground side of my power supply, and I have V0 here, everywhere that in my wires that I encounter no resistance, all has a potential of V0. And then everywhere with my ground wire, all has a potential of 0. So what that tells me is across each of these resistors, I have a potential difference of V0. So delta V1 for resistor R1 has to equal V0. Delta V2 for resistor R2 has to be V0. Delta V3 for resistor R3 has to be V0. And then for each of those components, you can state that the current is voltage over resistance with Ohm's law, right? So for I1 has to be V0 over R1. But V0 is the voltage of the power supply. So that means that when I add I2, it's also getting the full voltage of the power supply. And when I add in I3, it's also getting the full voltage of the power supply. So every one of these components is always getting the voltage of the power supply. So if I was to add a fourth one, that's going to add a fourth current. And so each of these resistors is going to get that exact same voltage of the power supply. And so what happens is my junction, I just keep adding more current. So that's going to cause I0 to go up. So you're adding more components, you're using more current. You're pulling more current from that battery to meet that need. The equivalent resistance, remember, for parallel was 1 over Req is equal to 1 over R1 plus 1 over R2 plus 1 over R3. So that's kind of weird because if you were to do that math, the more resistors you add, the smaller your equivalent resistance is going to get. Let's say that R1 is equal to R2, which is equal to R3, which is just equal to R. If I had a simple circuit that just had a single resistor R and my power supply V0, my current I0 is just going to be my total voltage over my total resistance, which is going to be V0 over R. Okay, that's for one component. Now, let's come over here and calculate our equivalent resistance for 3 of those. If I do that, I get 1 over Req is equal to 1, just a little delayed here, 1 over R plus 1 over R plus 1 over R. So what that's going to be is 1 over Req is going to equal 3 over R. So then when I flip this to find the actual equivalent resistance, I find that my equivalent resistance is equal to 1/3 of R. So even though I have 3 resistors in parallel, I end up with 1/3 of the equivalent resistance. So what that's going to mean is that current draw from that power supply is going to be I0 is equal to V0 over Req. That's going to be V0 over 1/3 of R. So that's going to mean that I0 is going to be 3 times V0 over R, which is going to be 3 times the current that was being pulled from that battery for just a single resistor. So that's what's kind of weird in your parallel circuits. So now we've looked at series, we've looked at parallel. What happens when you have a complex circuit that's a combination of these? So when we look here at this complex circuit, like I said, there is a parallel portion with R2 and R3 kind of embedded within R1. So what you can picture with equivalent resistance when you have a combination of series and parallel is you can picture that your equivalent resistance for R2 and R3, I'm just going to call that R23. I do that because I'm going to get several equivalent resistances that are possible here. So that tells me the equivalent resistance of just resistors 2 and 3. So R2 and R3 are in parallel. So we use the parallel portion of that equation to find our equivalent resistance. So that's going to be 1 over R23 is equal to 1 over R2 plus 1 over R3. So if I want to actually get rid of that reciprocal, I'm really going to have to get a common denominator in order to make that work. You cannot just flip those fractions upside down with that plus sign. So what I'm going to do is I'm going to multiply 1 over R2 by R3 over R3 and 1 over R3 by R2 over R2 to get my common denominator. So that's going to give me 1 over R23 is equal to R3 over R2 R3 plus R2 over R2 R3. then I can flip the reciprocal for that. So then I get R23, well, not quite. Here, hold on. Let's actually combine those before we flip. R23 for the reciprocal there is going to be R2 plus R3 over R23. R2, R3. Now flip. Now you got your common denominator. Now flip. So we get R23 is equal to R3 over R2 plus R3. Now let's say, just to kind of simplify and figure out what this did in our head, okay? I'm going to assume, just for right now, that R2 equals R3, which is equal to, let's also make that R1, and that's just equal to R. So by putting these into parallel, if I just double check, if everything's equal to R, then the numerator is going to be R times R. The denominator is going to be R plus R. So that is going to be R squared over 2R. And if I simplify that, I'm going to get rid of the square, get rid of that. I just get R over 2. So even though it's all kind of funky, my equivalent resistance is still going to be lower in parallel than if I had just one of those. Okay, so this still represents an equivalent resistance that's lower than either R2 or R3 in its own. Now, what this allows me to do, I found this equivalent resistance R23. I can picture replacing R23 with a single resistor and I'm going to take that parallel branch and I'm inserting this new equivalent resistance R23 that has this value in to replace it. And then what I have is the equivalent resistance R23 is replacing that. I now have a series circuit because I have one loop. So if I wanted to find the overall equivalent resistance of this circuit, and that's going to be for my series circuit with R1 and R23. They are in series with each other. So my overall equivalent resistance in series just adds. So REQ is going to be R1 plus R23. So REQ is going to be R1 plus, I found R23, that's going to be R2, R3 over R2 plus R3. And so that's going to be my overall equivalent resistance. Now, let's just go back really quickly and remember, if I had assumed that all of those resistors were the same, then that is the same thing as R plus, remember this guy was just R over 2? And so that would give me an overall resistance of 3R over 2. If I had just the parallel circuit, where they were all in parallel, my equivalent resistance was R over 3. Just the series circuit would be 3 times R, because they would have all added up. So this complex series circuit is kind of in between. It's less than if it was a pure series circuit, but it's more than if it was a pure parallel circuit. So it's kind of this hybrid between those. So that's how you can then kind of analyze these circuits in terms of equivalent resistance. Now, what about the loop and junction rules? How would we do those? So if we were looking at the junction rules, let's look at the junction rule for current. If we picture we have I0 coming out of my power supply, R1 is going to have a current coming through it, I1. Because there's no junction between the battery and R1, it's going to have a current I1 that is equal to I0. Because there's no junction. And then that current, that same current I1, or I0, however you want to call it, is coming into a junction here, and then it's splitting and going through R2. I'm going to call that one I2 through that branch, and I3 through this other branch. So I can see that because I have a split, I1 is going to be the sum of I2 and I3. So that means that I1 is also equal to I0, so that's going to be I2 plus I3. Now, if R2 and R3 have the exact same value, then that current is going to split evenly. But in general, current takes the path of least resistance, or more current will flow through less resistance. So if, for example, R2 was bigger than R3, then I would get more current through R3 and less current through R2. So I2 would actually be smaller than I3, but they would still have to add up to equal I0, because then they're going to come back together here, and at this junction, we have to have I0 coming back into our power supply. We can't have more going in than going out. Okay, that would not be conservation of charge. So that also tells me from this junction that I2 and I3 also have to add and combine back to I0 when it comes through, but they don't have to split evenly. So that's kind of what we can learn from our junctions. If I want to analyze the loop rule using voltage, I still need to make some assumptions about the direction of current. So if I hadn't already thought about the current before using the junction rule, I would have to pick a direction for current. Now, because I know that my conventional current is going to be coming out of my power supply, I would just assume, even if I didn't know, if my circuit got complicated, I would kind of pick a direction of current through each of these. Now, this is a nice simple circuit, but you'll see in the next lesson that we're going to see things with multiple power supplies where you may not know automatically what direction the current's going to be going. So either way, if you're going to use kind of that loop rule, you have to pick a direction of current. And then what you do when you have these complex circuits is you start at your power supply and you create a loop. So I'm going to create a loop that goes through R2. And that loop is going to come back around. I'm going to call that loop 1. So with loop 1, my V0 is going to act as a voltage rise because it's going to be a power supply, right? It's supplying power. So I'm going to go plus V0. And then as my current goes through, once again, I'm going to assume that I have V0 here at the start. And I haven't encountered any resistance, so that's going to be V0 there. So then I'm going to have a drop in potential across resistor R1, so that that point right there is going to be V0 minus delta V1. And then I'm going to come here, and this whole wire must also have that same potential. So when I get here on this part of the loop, that part of the loop right there has to be V0 minus delta V1. And then over here, I'm going to have another voltage drop of delta V2. So that point has to be V0 minus delta V1 minus delta V2. And that has to be the same that goes all the way through this wire back here to where zero potential is. So that has to add up to 0. So that tells me that my V0 minus my delta V1 minus my delta V2 has to add up to 0. So V0 has to be delta V1 plus delta V2. So I have to know that those voltage drops have to add up to V0. Conservation of energy. So then what I can do is I can pick a different loop that goes through R3. So similar idea, I'm going to come here, but I'm going to split to the right this time and come through. With V0 here, coming all the way to where R1 it is, that's going to be V0. Then we're going to have a voltage drop of delta V1. So this point right here is going to be V0 minus delta V1. And that's going to be the same when you come here to this junction, it splits off here. So that point is going to be V0 minus delta V1. And then we're going to come across and we're going to have a delta V3 drop there. So that next point is V0 minus delta V1 minus delta V3 as we've lost energy to R3 to heat. So then we're going to come out of there, come all the way back around to our 0 side. So that tells us that for loop 2, V0 minus delta V1 minus delta V3 has to add up to 0. So V0 must be delta V1 plus delta V3. Now when you compare these together, you can line them up and we can see that we have V0 in each of these equations is equal to V1 plus V2. Or plus V3. So that tells us that delta V2 has to equal delta V3. And that's really, really important because even though we are in this complex circuit, when we look at these branches here, I have a branch here that involves R2, that's going to be delta V2, and then we have this branch here that includes delta V3, that's going to be our delta V3. Those are still in parallel with each other, so therefore they are going to have the same voltage drop across them. That tells us that the voltages in parallel branches are equal. So even though they're not equal to V0, they are equal to each other. They're not equal to V0 because there's already been a voltage drop with R1 before even getting to V2 and V3. But in that branch, those voltages are in parallel. And they have to add up in series to what they are with delta V1 because they are that parallel section is in series with R1. So you can see how we can learn a lot of information about our circuits with our junction rules and our voltage rules. And then don't forget, for every single component, you can still do a rule for Ohm's law. So you can write an Ohm's law for delta V2, for delta V3, for delta V1, and for V0 for the power supply. So hopefully that gives you kind of an idea of how you might start approaching complex circuits that involve both series and parallel by applying the rules for series and parallel in pieces along with the junction and the loop rules. Have a great day.